This lesson is going to look at the nomenclature of simple compounds, simple inorganic and organic compounds. The organic compounds we're going to look at are going to be your basic hydrocarbons. We're not going to look at organic compounds that have many of the very common functional groups, such as the hydroxyl group or the carboxylic group. Now for inorganic compounds, the first ones we're going to look at are the ones containing monatomic ions. These are also called binary compounds, where you have just a metal ion and a non-metal ion. The way in which we name them, the cations are just going to be the name of the metal. We will often include a Roman numeral for those that have multiple oxidation states. The anions, since it's just a simple non-metal, just a single non-metal atom, with a charge on it, we are going to change its name to contain the root form plus add an IDE. A quick couple of examples. Your very basic NaCl, which is referred to as sodium chloride, is the name of the metal. The name of the nonmetal chlorine is altered to have the IDE ending. It doesn't matter how many there are. This would be magnesium chloride. You could have sodium oxide. The number of ions does not appear anywhere in the name. If you have a substance that contains a transitional metal, such as iron, which can have multiple oxidation states, we're going to have to name it including the oxidation state. So iron 2 nitrate. Now right there in my example, instead of having just a basic anion with an IDE ending, I already jumped to one that has a polyatomic ion. The nitrate ion is a polyatomic ion because it is a group of atoms with more than one atom together with a charge. And you'll see that in this series here, your nitrate has 3 oxygens. In the same series, nitrogen, oxygen, only 2 oxygens with the same -1, you change the ending to ITE. So whereas the IDE ending up here is typically found for monatomic anions, you're going to see endings of ATE and ITE for polyatomic anions. If you have a series that contains a change of more than just 2, by the way, the typical way of doing it is the ATE is reserved to the one that is the most common oxidation state. So here we have chlorate with 3 oxygens, but we also have an extra oxygen here, so we have to keep the AT ending, but we put perchlorate. When you have 1 fewer, again you see the IT ending. If you have 2 fewer, we have to keep the IT ending, but we have an additional prefix, the hypo prefix. And so this particular chlorine oxygen oxyanion is one in which we see a series of 4 and how the name progresses through that. Just like I had in the previous example, when you have one of these polyatomic ions, it doesn't matter how many there are, just like in the previous ones. We are just interested in naming the two ions. So we have magnesium. This is not a transition metal, so it does not need a Roman numeral, does not have more than 1 oxidation state, and the polyatomic ion is phosphate. Just so that you're aware, you can have polyatomic ions that have other endings besides the ATE and the ITE. A good example is the cyanide ion, so this would be sodium cyanide. Now in naming acids, there's actually 2 different types of acids reflecting 2 different ways of, or resulting in 2 different names for them. If you have a binary acid, which means you only have 2 elements in it, such as HCl, the way we name this is to have a hydro prefix. The root comes from the nonmetal, in this case the chlorine, and then you add IC, so this would be hydrochloric acid. I put in here the inorganic name. You might see it written as hydrogen chloride, but usually when it's named in its acid form, hydrochloric acid. If you have hydrogen sulfide, again, when we name it as an acid, since it's binary, we start off with the hydro prefix. We are going to, instead of dropping the ending, we're going to leave it as sulfur, but add the IC. Perhaps it's just because of the way it sounds, but that is really stuck where you keep the whole name for sulfur. Same thing happens with phosphorus, so in this case it's hydrosulfuric acid. Not to be confused with the oxy acids, which have a polyatomic ion in it. The way we name this is you do not have the hydro prefix. So while the inorganic name would be hydrogen sulfate, when we name it as the acid, I have never heard it referred to this. You always hear it referred to as the acid name. So this would be sulfuric acid. Again, no hydro prefix. And the reason why it has an IC ending is because this is the sulfate ion. If we had H2SO3, where it would be hydrogen sulfite, this time we change the ending to OUS, so this is sulfurous acid. So ITE endings result in an OUS ending. One more example, H2CO3, hydrogen carbonate. We take the ending, since it's the ATE, we change it to the IC ending, so this is carbonic acid. Now, as I mentioned in the introduction, this is going to be a very brief introduction to a brief overview of naming of organic compounds. We're only going to look at the simple hydrocarbons. So what I mean by a hydrocarbon is just a compound that contains carbon and hydrogen. So depending upon the number of carbons in the substance, then we are going to name it with a certain prefix. If you have a substance that only has one carbon in it, then we're going to use the meth prefix. If it has two, such as CH or C2H6, and its structural formula is two carbons bonded together with with 6 hydrogens off of it. All of them are single bonds, and because they're all single bonds, this is what's referred to as an alkane. And with two carbons, it's going to have the eth prefix, and just like the ane ending in alkane, we name it ethane. If you have a substance that has a double bond in it, so this would be C2H4, the addition of a double bond is going to reduce the number of carbons by 2. In our structural formula, we would see the double bond. We have the 2 hydrogens on each one. Since it's still 2 carbons, we'll have the eth prefix, but now this is going to have the ending ene, because a substance with a double bond is referred to as an alkene. Last example, let's say of this particular substance, let's say that we had C2H2, which means that our substance must have a triple bond, and the 2 hydrogens are off of each carbon. 2 carbons, you have the eth prefix, but this is an alkyne, so we refer to it as ethyne. I'll put one other simple one in here. Just let's say that we had a substance that was C6H12. Now actually when we get up to the larger ones and I just write down C6H12, there's a lot of different ways in which we could write the structural formula. For this particular one, I am going to make it a ring structure so that we have 6 carbons in a ring. This is what's referred to as a cycloalkane. And on each of these carbons, we are going to stick 2 hydrogens. And for simplicity, what we start doing is, instead of writing in all of the hydrogens, you'll often see just a line, a stick, with nothing on the end of it. Whenever you see that, that means that there's a hydrogen off of there. And so if you were to count these all up, you would find out that there's 12. Total of 6 carbons, so we have a hexane. They're all single bonds, that's why the A and E, but we want to include something in the name that tells us that this is a ring structure. So at the beginning, we add the fact that it's a cyclohexane. If this had been C6H14, just a straight chain of 6, it would have been hexane. And lastly, what we're going to do is we're just going to add some branches to these substances. We're going to take these same hydrocarbons and just, instead of having a straight chain or a simple ring, we are going to put some side branches on it. So let's say that we had a substance that had a total of 6 carbons in it in a straight chain. And to this chain, we are going to add 1 single carbon branched off. Now, as I said before, we can simplify our structure. We know that there has to be a total of 4 bonds off of each carbon. And in this case, since it's a hydrocarbon, all of them are going to be hydrogens, and it would be a little complicated to draw all of the hydrogens in there. And actually what I've done is I've done this in the structural formula. I've drawn the structural formula into the chemical formula. So this should be C7 H16. Now, how do we name this? Well, what we're going to do is we're going to find the longest straight chain, not including any branches, and what we do is we just count them off, and we'll see that there's 1, 2, 3, 4, 5, 6 carbons here with a branch. It actually doesn't matter how we do this, because I could start my branch here, go 1, 2, 3, 4, 5, 6 with a branch off the side. It's the same thing. So the straight chain is 6 in a row, so that makes this a hexane. But we have to indicate that there's a branch off of it. And this branch contains 1 carbon. So 1 has the prefix meth. And being a branch, we are going to say that this is a methyl. This is a methyl branch. Now, the branch occurs on a particular carbon. Right now it's on this carbon. It could have been on this carbon or this carbon. It could have been any of these carbons except for the end. And so what we do is we have to indicate which one it is. And so what we do is we have to number off the carbons. And what we do is we always start to number the chain from the end closest to where the branch is. So this will be carbon 1, 2, 3, 4, 5, 6. The branch occurs on the second carbon, so this would be 2-methylhexane. Let's look at another example of that. Let's say that we had a compound that had 5 carbons, and we are going to put a branch here, and we're going to put, how can I do this? I'll make it too messy. Let's put a 2 carbon branch here. Now, this is actually a little tricky. It looks like we have a straight chain of 5 with 2 branches off of it. But when we name this, what we're doing is we're looking for the longest string of carbons. So if we look at it this way, 1, 2, 3, 4, 5, 6, there are 6 carbons here in a row. So what we do is that makes it, again, a hexane. And it has 2 branches. If this is our chain, there's a branch here and there's a branch here. Well, where do we number it from? If we start from this side, this would be 1, 2, 3. The branch would start on 3, 4, and it would also occur on 5. But we start numbering from the end that's going to give us our lowest number for the first branch. So this would be 1, this would be 2, 3, the other branch occurs on 4. So we have 2 single carbon branches at 2 and 4, and since there's 2 of them, we're going to call them 2,4-dimethylhexane.